Hi, in this video I'm going to show you how to create a molecular model using the University of Illinois software called VMD, which stands for Visual Molecular Dynamics. So I'm going to go to my Start menu and open VMD, and you'll notice that several windows open. There's this main window where you can get to all of the functions that are within VMD. There's a DOS window that's acting sort of like the command line, telling us everything that is going on to make the program VMD run. Not so important for us to keep track of, so I'm going to minimize that. And there's this main display window. I like to make that as large as possible because that's going to be where our structure is displayed. Okay, so the first thing to do is to go to File, New Molecule. I'm going to browse my computer, and as we talked about in the last video, we created a directory in our documents called casein kinase. And here's my structure 1CSN. It should load here in the file name. And I'll just click load, and that's the only structure I'm going to load, so I'm going to close this window. And you can see now that we have our structure loaded. And we can move it around by using the left mouse button. If we click and hold, we can rotate it around and flip it end over end. We can also, if we click in the center, we can rotate it this way. I can zoom in and out by rolling the mouse forward, zooms in, rolling the mouse backwards, zooms out. I'm going to zoom in a little bit. And we can see here that we have our X, Y, and Z coordinate system. As we talked about, the PDB file lists all of the atoms in our structure by their X, Y, and Z coordinates. And so that's just telling us those coordinate directions within the software here. Okay, so what we want to do is create some sort of visually appealing molecular model that highlights some important parts of the structure of the enzyme that we're studying. So what I do is I go to this main window, click on Graphics, Representations, and that will open up a new window. And what I have here is a list of all the representations. You can have almost as many as you want. And what we have now is just everything shown as lines. So the selection is all. It's colored by the name of the atom, so you can see that there are reds for oxygen, blue for nitrogen, sort of a teal color for the carbon, some yellows in there for sulfur. So the color name here corresponds to that, and its lines are drawn for each of the bonds that are present. What we can do is we can change this to something that looks a little nicer, at least in my opinion. I like the cartoon style or the ribbon style, so I'm going to select New Cartoon, and that will give us this nice representation that's no longer colored by each of the atoms, but just shows us a single color ribbon structure. And I'm going to change the color by selecting the coloring method. I'm going to select color ID, and I like blue, so I'll leave that on blue. And the next thing I'm going to do is I want to highlight, there's a sort of an unstructured looking loop here that's hypothesized to be responsible for activating or inhibiting the function of this particular enzyme by moving back and forth somehow. That's still the subject of some pretty intense research, and part of what we're doing with our genetics class on this project. So what I want to do is I want to highlight that loop in a different color just to show that that's something structurally relevant. And to do that, what I need to do is go into the selected atoms here, and I'm going to type a list of atoms to highlight, and I'm going to do that by typing res ID as one word, and it's numbers 154 to 181, and I'm going to click Create Representation, so that creates a new representation here. I have the previous one that has everything for the selection, and now I have my new one. I can make this window a little bigger. That's res ID 154 to 181. I'm going to change those to the color red. So now we can see that we have this loop and it's colored red. Now I'm going to talk in just a minute about these keywords such as res ID and all here. But just to say first, res ID is going to be the actual amino acid number that is in the list of amino acids from the N terminus to the C terminus in your protein. And so for this particular crystal structure, it started with residue 6. That would be res ID 6. And it goes up to, I believe, 300 for the enzyme itself. There's another keyword that we'll see in just a moment called residue. Residue is the actual list in the order in the PDB file, and it starts counting from 0. So if I were to type in residue for my selected, what that's going to do is, it's because this particular crystal structure is missing the first 6 amino acids, it's going to shift my red highlight by 6 amino acids if I do this. So you can see that it shifted from over here, it took 6 away from here and shifted them this direction. And that's simply because this particular structure is missing the first 6. If it were the entire structure, the res ID and residue would correspond to the same sets of amino acids. So I'm going to go back to res ID, shift that to the correct set. And then I want to point out a couple of other structural features. One is that we have ATP, so I can type res name and give it the name ATP. There's only one ATP on this crystal structure. And so if I do that and create a representation, it's only going to show me one ATP molecule. However, ATP doesn't have excuse me, doesn't have a ribbon structure, so I need to change this to something that shows the atoms or the bonds of the ATP. So I'm going to select CPK, and I'm going to change it back to coloring it by its name. And now we can see that we have here, I'm going to zoom in, we have ATP with its phosphorus atoms, oxygens, carbon, some nitrogen as well. All color-coded nicely for us. I'm going to also highlight things that go by res name Mg for magnesium. The magnesium in this structure helps coordinate the ATP to the crystal. I'm going to create a representation of that, and we can see that this sort of pink colored atom shows up. That's the magnesium. Now what I want to do is, instead of increasing the list of things here, what I want to do is I want to add magnesium to this so that I can shorten my list of representations that I have here. I can do that using logic statements such as and or. So if I type res name ATP or res name Mg, I can type that in and then I can delete this representation, but what we see is that the magnesium stays there, and it actually shows the coordination of the magnesium with the ATP. I can take that one step further and type or res name SO4 for sulfate, enter, and what we see are a couple of sulfate molecules show up here and here. Those were important components to the buffer solution in getting this particular enzyme to crystallize. That's often the case, that some ions are needed to help rigidify the protein structure in order to get the crystal to actually form a nice crystal that can be then measured using X-ray or neutron or other kinds of diffractive techniques. Okay, so I want to add one other thing here that I'm just going to show exists, but then I'll delete them because you'll see that this causes the structure to look pretty messy. I'm going to show you that there are also some water molecules that are part of this crystal structure. So I'm going to create that representation. And you can see all of the water molecules show up in red, which are just some oxygens. They're not actually shown as water molecules with the H2 and the O. That's because most crystal structures don't include hydrogen atoms. However, further along in this tutorial, what you'll see is that the hydrogen gets added in by VMD in order to do the molecular dynamics simulations. Okay, so I'm going to delete that because, like I say, to me it looks a little bit messy, and I'm going to leave it like this and even rotate it around a little bit so that we can see that ribbon structure that we're interested in better understanding. I wanted to talk a little bit more about these keywords. As a new user, you won't know those keywords, and what you can do is click on this selections menu, and then you'll notice there's a box here that says keyword, and we can scroll through and see all different types of keywords that we could use to assist in creating our molecular model. So for example, here is residue that we were just talking about, and it starts from 0 and goes to something like 399. So there are 400 total residues in this structure. That includes the ATP, the magnesium, the sulfate, and all of the water molecules. If we were to only look at the residues associated with the protein, that would be, I believe, 300 or maybe 298 residues. I can't remember exactly, but this list includes everything, not just the protein. And then this other keyword, res-ID, that we've been using, we see that it starts at 6 rather than beginning with the first amino acid. So this is the actual amino acid number in the sequence of amino acids that are part of the protein. But it also includes the water in that list. And if you remember from the PDB file, all of the water, magnesium, ATP, and sulfate molecules were at the end of the file. They were the residues that came after the enzyme. If you don't remember that, you can always go back and look at the text that's in the PDB file. So I really recommend going through and playing around with some of these different keywords and seeing what they do. It'll help you get a better understanding of how to create good molecular models for identifying the parts of structures that are interesting to you. And as well, you get more familiar with the software so that you're a better user of it. Up next, what we're going to do is select a couple of amino acids that we believe are important for locking this loop, this activation loop, into its different conformations, which create the activity or the inhibition of the enzyme. And we'll show you how to measure the distance between those, because that may be the structurally relevant parameter. If those two particular amino acids come in close contact with one another, they can form an ionic coupling between them because they are charged residues. And so we'll look at that in the next video and just see how we can do things like make measurements between two different amino acids.